physics of scales and pitch harmonics. Before being able to understand much of the physics of music, it is necessary to have the basic understanding of scales and how they work. The tone currently being played is A440, the standard tuning pitch of musical instruments. It is essentially the reference pitch for all other frequencies, or pitches, in a sequence called a scale. There are many types of scales and quite a lot of theory behind them, but to keep things simple, we have to only refer to two of them, C major and the chromatic scale. In reference to a piano, the chromatic scale is simply every key, and C major is every white key, starting on C. There are two classifications of scales that exist, the just scale and the equal tempered scale. A just scale is the most natural form of scale, and the notes in it are related by simple ratios. But just scales are very impractical to use in non-choral ensembles because they do not have consistent tunings. The notes of the just scale are related to the fundamental, or lowest frequency, by rational numbers, and the steps are not equally spaced. The just scale also includes many notes that are not actually used. Instead, most music is made with the equal tempered scale, which uses constant frequency multiples between the notes of the chromatic scale. This basically means that rather than using the natural ratios in the just scale, fixed increments are defined between each note. The frequency of each note in the chromatic scale is related to the frequency of the adjacent notes by a factor of the 12th root of 2, or 1.0594630944, etc. These increments between notes in a scale are known as steps or semitones. For example, the chromatic scale is comprised entirely of half steps, whereas other scales are comprised of particular sequence of steps, such as the C major scale, and all major scales, in fact, which has the pattern whole, whole, half, whole, 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 half. When it comes to using scales practically, combinations of notes related by ratios of small integers, such as fifth, or 3 halves, or third, 5/4, are the best sounding. To hear the difference between a just scale and an equal tempered scale, pay attention to the patterns formed by the differences in pitch, or beats, as C major is played in both just and equal tempered tuning. Now it is important to understand what exactly pitch is. In its simplest terms, pitch is just the frequency of a tone. Higher frequencies create higher pitches, and lower frequencies create lower pitches. As mentioned, certain combinations of pitches can create a very pleasing sound known as consonance, while others create a very clashing and unpleasant sound known as dissonance. This has to do with the ratios of pitches and frequencies, known in music as intervals. The four most common intervals are the octave, which is a 2-to-1 ratio, the third, which is a 5-to-4 ratio, the fourth, which is a 4-to-3 ratio, and the fifth, which is a 3-to-2 ratio. In reference to the C major scale, the root, or origin of the scale is quite appropriately C, or 1. An octave above C, or 8 white keys to the right, is also C, but with twice the frequency. A third above C is 3 keys to the right and is the note E, which has 5/4 the frequency of C. The fourth is 4 keys to the right of C and has a frequency 4/3 that of C. Finally, the fifth is 5 keys to the right of C and has 3/2 the frequency of C. Now that you understand all this technical jargon, we can move on to the main topic, pitch harmonics. Knowing how it is that pitches and scales work makes it far easier to understand the physics behind being able to play something like this. This interesting playing style is possible because of the physics of vibrating strings and waves. On a guitar, a player creates sound by strumming different strings of varying lengths. The lengths of these strings can be adjusted by pressing down on the different frets on the neck of the guitar or by tuning the guitar. The shorter the length of the string, or the higher the tension on the string, the higher the frequency produced. These vibrations from the strings can be amplified either acoustically or electrically. To produce pitch harmonics on a guitar, a different approach is used. Rather than pressing down on the strings at a certain fret, the player gently touches the strings with their fingers over the fret. However, this will only work at certain locations, the 5th, 7th, 12th, 19th, and 24th frets. It is also important to note that the highest pitch is the 5th fret and the lowest is the 12th fret, and then rises in pitch again until the 24th fret. Why is this? It has to do with the behavior of vibrating strings. Waves travel on a string at the speed of v depending on the tension T of the string and the mass density ρ of the string. This can be shown in the equation v is equal to the square root of T over ρ. For any string of length L, any vibration created on a string can be broken down into a series of standing waves or modes. These modes are labeled with integers n, starting with n equals 1 or the fundamental mode. N equals 2 is the second mode and the first harmonic. N equals 3 is the third mode and the second harmonic, and etc. Things start to get a bit confusing around here, but we'll try to explain as clearly and simply as possible. The mode of a wave can be calculated or graphed using the function y sub n of x is equal to a sub n of sine times n pi x over L, where y sub n x is the height of the wave as a function of the position x on a string. A sub n is the amplitude, and n is the mode number.
If we look again at this diagram, we can see that there are nodes, or points of zero amplitude, at intervals of L over N along the length of the vibrating string. These points are what allow pitch harmonics to work. When a player plucks a string normally, the string will vibrate with a combination of all the modes in this very intimidating equation.
Y, x, comma t is equal to the sum of infinity as n approaches 1 of a sub n sine times pi n x divided by L times cosine pi v n t divided by L.
All this equation does is tell us the relative sum of the amplitudes and the modes the plucked string can produce. However, for n equals 1, the fundamental mode, the amplitude will always be greatest and will therefore always overpower the other harmonics. These harmonics are not lost, however, and support the fundamental in creating the unique sound of the guitar. Now we've come to the point we've been building up to! Pitch harmonics! You may be asking yourself, if the fundamental overpowers all of the other harmonics, how can we play them and hear them? Luckily, we've already answered this earlier. Gently touch the strings at certain points and you'll isolate specific harmonics. More specifically, touch the string at the location of a node and you will block out the fundamental, allowing just the desired harmonic to be heard. Nodes are located halfway along the string, the 12th fret, a third of the way along the string, the 7th and 19th frets, or a quarter of the way along the string, the 4th and 24th frets. These are the first, second, and third harmonics, respectively. According to the equations mentioned earlier, you could theoretically play infinitely more harmonics, but past the third harmonic, there's just not enough energy in the vibrating string to produce an audible sound. Now that we've survived all this complicated math and whatnot, let's take a break and listen to an excerpt of Stephen playing a song on the bass that is largely based around pitch harmonics, which is Portrait of Tracy by Jacob Astorius. Unfortunately, pitch harmonics are difficult to pick up well on an iPhone mic, but you can get the gist of it.
Good enough.